Well, now that we've learned some of the very basics of ionic bonding and covalent bonding, we're going to get into a lot more of the detail, specifically in covalent bonding today. So, just as a review, how do atoms bond together? We talked about two ways, but we're going to get into a couple of other ways in a second here. The four main ways that atoms bond to form compounds are: 1. Ionic bonding. Electrons are transferred from one atom to another, and then they become charged particles and are attracted to each other with an ionic bond. The cation and anion are attracted to each other. Covalent bonding, in which electrons are shared between two atoms because the electronegative pull of each of those atoms is not strong enough to actually take an electron, and so they share them. And those are the two that we've talked about so far. Additionally, there is metallic bonding, in which electrons surround atoms in an overlapping lattice. And network covalent bonding, which is a giant covalent molecule with a repeating pattern, creating a network of atoms. So, for example, you'd find network covalent bonding in a diamond, which is made of repeating patterns of carbon atoms covalently bonded together. This pattern makes the compound much harder than a typical covalent compound, which you, of course, know that diamonds are much harder than other covalent compounds like wax, for example. And we'll get into metallic bonding now in a little bit more detail. So, how are electrons shared in a metallic bond? Atoms of a solid metal form a lattice with valence shells that overlap. So we did talk about a lattice, crystal lattice network in our discussion of ionic bonds. This is a different kind of lattice. First of all, we're not talking about a compound, we're talking about a solid metal. And these atoms of a solid metal here, so just one element, lots of atoms of one element, are stacked up close to each other, and the electrons are surrounding them. And this is known as the electron sea model, because the electrons are sort of floating around in a sea around these cations of metal. The electrons are able to freely move, creating metallic cations as they move from one atom to another. So they're attracted from one atom to another because the atoms are so close together. And when they leave one of the atoms, that atom becomes a cation, and the electron moves on to something else nearby. And so then those cations are the positively charged particles that are left behind with that sea of electrons surrounding them. And when a metallic cation is attracted to the freely moving electrons, a metallic bond forms. And the sea of floating electrons absorb and re-emit photons very easily. And that interaction with light is what makes metals shiny. Also, the sea of electrons is what's responsible for allowing solid metals to conduct electricity so easily, because they're able to move freely. So, what are the properties of metals? The strong metallic bonding caused by the sea of cations and electrons causes several different physical properties. Metals have high boiling points because they are so closely condensed together. They are malleable, which means that they can be hammered into sheets. So the layers of cations and electrons in metallic bonding allows for them to slide over each other when force is applied. So that contributes to the property of malleability. Ductility is the ability to be drawn into thin wires, again, because they're able to slide past each other. And as we mentioned, they are conductive to both heat and electricity because of that freely floating sea of electrons that can transmit electricity. And they are also quite strong because they are so closely packed together into the lattice structure. The metal cations can move past each other, causing properties like malleability and ductility. Because of the strong attraction between the sea of electrons and the cations, metals are strong and they're not easily converted into other states, so that contributes to their high boiling point. And on your notes, you have a space to draw the electron sea model, so I just thought I'd put that back up there. So let's shift into a discussion now about covalent bonds in the form of diatomic molecules. So one example of a covalent bond is a diatomic molecule. And diatomic molecules are formed when two of the same type of atom share electrons. So exactly the same element, exactly the same type of atom sharing electrons, which increases the stability of the atoms. So an individual fluorine atom has 7 valence electrons, but if it shares an electron with another fluorine atom, then that provides them stability because now their outer valence shells are full. And this is a diatomic molecule, di meaning 2, so 2 atoms of the same element here. And here are the types of diatomic molecules that exist naturally. We have hydrogen, H2, nitrogen, N2, oxygen, O2, fluorine, F2, chlorine, Cl2, and bromine, Br2, and iodine, I2. So these are important to know, and I'm going to have you mark those on your periodic table as diatomic molecules, however that makes sense to you, or you can write them at the top of your periodic table, but these are important to know because you'll need these throughout the remainder of the course, and you will need to have those written down or memorized somewhere. And a good way to remember this, if you need to memorize it, is Hofbrinkel. So if you can remember Hofbrinkel, this will help you remember all of the diatomic molecules. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So this is a great little mnemonic to help you remember all of these because you will need to know these for the entire course. In summary, electrons are shared in covalent bonds. Some covalent compounds form a network, while some occur in diatomic molecules. In a metallic bond, electrons are freely shared, which causes the physical properties of metals. What is the octet rule when we're referring to bonding? The octet rule refers to the tendency of atoms to bond until 8 valence electrons surround the atom. We also discussed this as noble gas envy in the previous unit. Now we're going to get a little bit more specific here. We're going to refer to it as the octet rule because we're looking for 8 valence electrons. Atoms with 8 valence electrons, even shared electrons, can add to that 8, create a more stable compound. So here's a molecule of methane, which is CH4. This is the common name. It is actually carbon tetrahydride, like we had discussed in a previous unit. So if this molecule of methane has 4 hydrogen atoms around the outside and a carbon atom in the middle, the central carbon atom only has 4 valence electrons because if you look back at your periodic table, carbon only has 4 valence electrons. It has 6 electrons, there's 2 core electrons, and then 4 in the outer shell. So by sharing electrons with 4 different hydrogen atoms, it can have a full valence shell of 8 electrons. And that's also helpful for hydrogen because now it has a full valence shell of 2 in that first energy level. But how many electrons can actually be shared? We've been talking about sharing electrons, but not necessarily numbers. Well, covalent bonds can be single, in which 1 pair of electrons is shared, double bonds, in which 2 pairs of electrons are shared, or 4 electrons total, or it can be a triple bond, in which 3 pairs of electrons are shared. In our previous fluorine example, the sharing of 2 electrons makes a single bond. So we're sharing these 2 electrons here. Sometimes we illustrate that by overlapping these 2 atoms. Either way is the same, but we write this single bond as a line very frequently, that these 2 electrons are being shared. So this is a single bond. And the length of the bonds is determined by the number of bonds. So bond length is the distance between the centers of the 2 covalently bonded atoms. And the bond length decreases as the number of bonds increases. So these dots here would represent our 2 different atoms that are being bonded together. This is a single bond. This is a double bond, which would be sharing 2 pairs of electrons, or 4 electrons total. And this is a triple bond that would be sharing 6 electrons total. Notice that the triple bonds are much shorter because those nuclei are being pulled closer together, and they're also stronger than double or single bonds. How are bond length and bond energy related then? Well, bond energy measures the amount of energy required to break a bond. And you might have learned in the past that when you break a bond, energy is released. So the shorter the bond, the more energy is required to break the bond and to separate the 2 atoms. Again, they're shorter and stronger and therefore harder to break. Compounds that are hard to separate are known to be more stable. So, for example, N2, or diatomic nitrogen, is found in the atmosphere, and it's very hard for organisms to break that down. There's only few organisms that do that because the N2 molecule is a triple bonded molecule, and so they are very stable and difficult to break. So stop now and work on filling in the arrows in your guided notes. The answer to that is on the next slide, but I want you to think about it rather than just writing down exactly what's on the slide. So as the number of bonds increases, the bond length decreases, but the bond energy increases. So we've got a single bond at this end, double bond in the middle, triple bond at this end. The length of bond is increasing as we go from right to left. Single bonds have the longest bond length. Triple bonds are the shortest, but the energy increases from left to right because single bonds have the least amount of energy. Triple bonds have the greatest amount of energy required to break them. In summary, atoms bond according to the octet rule. This can involve sharing 1 or more pairs of electrons. As the number of electrons shared increases, the bond energy increases, but the bond length decreases. So continuing on here with covalent bonds, how can molecular structures be represented? Several different types of models can be used to represent molecular structures and their covalent bonds. Remember, when 2 atoms or 2 or more atoms are covalently bonded together, we call that a molecular structure. So molecular bonds and covalent bonds are sometimes used interchangeably. The molecular formula shows the number of each type of atom in the compound. So you're familiar with this one. This is just a chemical formula. Here we're talking about covalently bonded atoms, and so we're saying that's a molecular formula, but same thing. The structural formula, which is also known as a skeletal formula, is a simplified sketch of the atoms and their bonds. So here's an example of that. We've got nitrogen in the middle, and then we are showing single bonds here with these individual lines between nitrogen and fluorine. So that's a structural formula or a skeletal formula. Third, the Lewis structure is similar to the structural formula, but also shows valence electrons that are not represented by bonds, and we call those lone electrons. So we discussed Lewis structures and their valence electrons and how we write those when we discussed individual atoms, but you haven't seen them bonded together with other atoms at this point. So now we see bonds in here, single bond, as well as the remaining valence electrons. So this represents 2 electrons. We've got one coming from nitrogen, one coming from fluorine, but they're being shared. So this is 2 electrons, and then the remaining 6 around each element of fluorine here. And we call those lone electrons. And the space filling model is another way to write a formula. It uses colored atoms of different sizes based on the atomic radius. So this is NF3 here, just as the other versions were, but the nitrogen is now in the center as a colored ball, and then 3 hydrogens around the outside. Bonds are not shown in this type of space filling model. And finally, the ball and stick model shows the relative location of atoms in the compound and the bonds between them. So you can see here, similar to our space filling model, these atoms were around nearer to the bottom of this model, and they are in this one as well. So it does help to represent the location of those actual atoms, and we'll discuss how we can tell where they are and the location of those atoms in a minute. But this is the ball and stick model showing the joining between those two, the bonds between those atoms, as well as the individual atoms themselves as the spheres. So those are several different ways that we can represent molecules, and each one has a particular function, and so sometimes it's helpful to use one model and sometimes it's helpful to use a different one. What are resonance structures? Sometimes the same set of atoms can be arranged with more than one Lewis structure. Remember, a Lewis structure is when we are using the bonds as lines and the remaining valence electrons are shown around the outside. And this phenomenon is known as resonance. So these are the same atoms bonded together, but the bonding can be arranged a little bit differently. And so I'll show you an example of that. Here's O3 in one format, single bond here, double bonds here with our valence electrons around. And another format for that would be if the double bond is over here and the single bond is on this side. So these are resonance structures. So these ozone molecules, which is O3, show resonance because the location of the double bond can change. So same atoms, different arrangement. And as you notice, these still follow the octet rule because we have 2 electrons on this side, 2 covered by this bond, 2 covered by this bond, and 2 covered by this bond. So that's 8 total, and the same goes for these other atoms over here. So in summary, molecular structures can be represented by several types of models. If the structure of the molecule can occur in more than one way, it's known as resonance. So does a molecule's shape matter? Well, a molecule's shape really does matter because enzymes use different molecules as like a lock and key system. And so sometimes the enzyme will not recognize a molecule that's the wrong shape. Medicine requires molecules that are particular shapes so that your body recognizes them, or that you can substitute different molecules for the ones that your body naturally produces. But how do we determine what a molecule's shape actually is? Well, the three-dimensional shape of a molecule determines many of its physical and chemical properties, and we call the shape of a molecule its molecular geometry. What you've learned about valence electrons previously already and bonding is going to help you determine what the molecular geometry is for these different models. So water molecules are shaped like the image on the right, with bonds that are bent on an angle. Maybe you've seen this in biology class. Why are these bonds on angles instead of straight? That's what we're going to get into next. What is VSEPR theory? So this is an acronym which stands for valence shell electron pair repulsion. And so we use just the first letter of each of those words. And because you can't really pronounce VSEPR very easily, we call this VSEPR theory. So VSEPR models help us to look at two-dimensional Lewis structures in 3 dimensions. So we're converting a two-dimensional Lewis structure like you would write on paper into a 3-dimensional molecule that has a particular shape. Lone electron pairs repel other atoms and take up more space than bonded atoms. So if we look at the Lewis structure of this water molecule, you'll see we have lone pairs of electrons up here, 2, 4, and then we have 2 additional bonds here. So we've got our octet covered for oxygen. But these lone pairs of electrons at the top actually take up more space than these bonds of electrons over here in the covalently bonded electrons. Because the oxygen atom has unbonded electron pairs, they push the hydrogen atoms into a bent structure. So they're pushing these over so that we don't have them all separated by 90-degree angles. These lone pairs are bending the hydrogen away from them. The lone pairs are drawn closer to the nucleus than bonded atoms, so they take up more space. And that's what's creating this bent molecule here for water. What are the different shapes? So you're going to be tempted here to think that you need to just memorize what each type of the shape that each type of molecule is. And although you need to memorize these shapes for sure, you don't need to memorize which molecules are which shape. Your knowledge of valence electrons and bonding is going to help you determine what type of shape each molecule is. So our first shape is linear. And you can see here if we have 2 single bonds or 2 double bonds, we're going to have a linear shaped molecule. And the angle between the atoms is 180, or half of a circle, as you might imagine. An example of this is carbon dioxide. So carbon dioxide is going to be this molecule here, and it is a linear shape, so straight molecule. The second shape is trigonal planar. So tri obviously means 3. So we've got 3 atoms bonded around one central atom. They are all in the same plane. So if we were to turn this sideways, it would be flat, like a piece of pizza, let's say, triangular, but none of these are sticking up. They're all on the same plane. So we call that trigonal planar. And the angle between the atoms is 120 degrees, or a third of a circle. And an example of that is boron trichloride, with the boron being the center atom and then 3 chlorines around the outside. The third shape is trigonal pyramidal. And just as it sounds here, we're talking again about three atoms around a central atom. And in this time, we are forming a pyramid rather than them all being on the same plane for trigonal planar. We're forming a pyramid shape where these three atoms are being bent lower and away from some lone electrons up here. The angle between the atoms here is going to be 107 degrees. And an example of that is ammonium, which is NH3. Continuing on, we also have a bent shape, and this would be like your water molecule that we discussed earlier, where you have one central atom and two outer atoms with a significantly bent structure. Those atoms are being pushed away and closer to each other, away from these lone electrons that are found up here. The angle between the atoms is 104 degrees. And then finally we have tetrahedral shape, which is one central atom with four atoms around it, and 109 degrees between those atoms. And CH4 or methane is an example of this type of molecule. And this is arranged so that these are sort of in a pyramid at the bottom, and then there is an atom sticking up at the top as well. There are other shapes of molecules. These are the most common ones, and so these are the ones we're going to stick with for this unit, but just know that there are significantly more complex types of molecules as well. In summary, VSEPR theory predicts the molecular geometry or shape of a molecule. Electron pairs repel other electrons, with lone pairs of electrons taking up the most space. The basic shapes are linear, trigonal planar, trigonal pyramidal, bent, and tetrahedral. So I think when we're discussing covalent bonds, it's easy to assume that these electrons are being shared equally between the two atoms that are bonded together. So are electrons shared equally? Well, in nonpolar covalent bonds, the electrons are shared equally between the atoms involved. So nonpolar here meaning that there are no poles between the bond. It's not unequal, it's not polarized, it's evenly shared or equally shared between the atoms. Polar covalent bonds share the electron pair unequally. One of the atoms is more electronegative, meaning that it pulls the electron strongly, than the other, which causes uneven sharing. So here's my little graphic of the bond between oxygen and hydrogen. Oxygen has a significantly stronger electronegativity value. It pulls the electron harder, more strongly than the hydrogen atom does. And so, as you can see, like a tug of war, it's being pulled a little bit more towards the oxygen side. This is not being evenly pulled on both sides. So we call that a polar covalent bond. So this causes one side of the molecule to be slightly negative because it's got a stronger electron pull, and the other side to be slightly positive. So in this example of a water molecule, because the oxygen is more electronegative than the two hydrogen atoms, this side is going to pull more strongly on the shared electrons, causing it to be slightly negative, which we mark with this designation. And then this side of the molecule is going to be slightly positive. And that's the reason that water molecules stick together, creating some of the properties that are unique to water. Because the slightly positive side of one water molecule can be attracted to the slightly negative side of another water molecule, which causes things like surface tension and the ability for water to creep up little tubes like in plant stems. And you'll learn more about that soon. So the stronger electronegativity of oxygen is causing polar bonds here. So we have a choice between nonpolar and polar bonds, and because of this high electronegativity value for oxygen, this is going to be a polar bond, polar covalent. The more electronegative atom, which is oxygen here, has a slight negative charge, and the less electronegative atoms, hydrogen, have a slight positive charge. Polarity arrows show how electrons are moving within a polar molecule. So here you can see that the electrons are being shifted from the slightly positive side to the slightly negative side. And this is going to be the slightly positive side of the bond, and this is the partially negative side of the bond. So how do I determine whether a bond, a covalent bond, is polar or nonpolar? Well, differences in electronegativity values between the atoms reflect the polarity of the bond. So here, if we have a bond between carbon and chlorine, the electronegativity value of carbon is 2.5, and the electronegativity value of chlorine is 3.0. And so this is going to be a difference in electronegativity of 0.5. And so what exactly do we do with those numbers? Well, here's where the numbers came from. First of all, we have electronegativity values for all of the elements. So here's carbon, 2.5, and here's chlorine, 3.0. Remember, electronegativity values are increasing all the way from bottom to top and left to right up towards fluorine, which has the highest electronegativity value. Noble gases do not have electronegativity values since they don't draw in electrons. This is a chart that will be given to you. You don't need to memorize this, but you can see that these are the two values that we were using. And there isn't a clear distinction between ionic and covalent bonds, but there is a scale. Linus Pauling created an electronegativity scale to help determine bonding type and the strength of the bond. So our 0.5 difference here between carbon and chlorine is going to be found somewhere close to the value here, 0.5, and so it is in the polar covalent region. So those two electronegativity values are different enough that the electrons are going to be pulled strongly by one of those atoms, creating a polar bond. And ionic bonds are going to have a much larger electronegativity difference, but they have to be between a metal and a nonmetal. If we got any further down the scale here, the covalent bond would actually be nonpolar because the electronegativity values are not different enough to create that unequal tug of war of the electrons. So here we have sort of equal electronegativity values, and then they're becoming more unequal and then very unequal in the ionic category. And that's why one atom in an ionic bond is actually pulling an entire electron off of another. And so they're not sharing at all. But just as a reminder, they have to be between a metal and a nonmetal. So practice using the electronegativity values on the previous slides. Determine if the following bonds are ionic, nonpolar covalent, or polar covalent. So write down these pairings, and then I will go back to the previous slide that had the electronegativity values, and then you can subtract those values and determine what kind of bond they are. So pause the video, write these 8 pairs of atoms down, and then I'll go back. So you're going to use this set of electronegativity values to look up those atoms. Subtract, it doesn't matter. We're really taking the absolute value here, so it doesn't matter which one you use first. You're just finding the difference between the two of them. None of these values are going to be negative. So find the difference between those two values. Pause the video until you figure those out, and then we'll go back to the scale and you can determine whether they're nonpolar, polar, or ionic. Okay, and now use this scale to determine whether they're nonpolar covalent, polar covalent, or ionic based on those electronegativity differences that you calculated. Remember that to be an ionic bond, it has to be a metal and a nonmetal bonded together. Pause the video here, and then we'll check all of our answers to those questions in a second. Okay, so here are your answers. Hydrogen has exactly the same electronegativity values, so that is going to be a difference of 0, giving you a perfectly nonpolar molecule. Hydrogen and fluorine are polar covalent. Hydrogen and iodine are polar, verging on polar or nonpolar covalent. Very close in between those two. Sodium and fluorine are ionic, metal and nonmetal. Magnesium and sulfur are also ionic, metal and nonmetal. Hydrogen and chlorine are polar covalent. Sodium and chlorine are ionic, and carbon and sulfur are nonpolar covalent. So how does shape affect polarity? How does the shape of a molecule affect its polarity? Well, the shape of a molecule can determine its overall polarity. So we're discussing here the polarity of the whole molecule rather than just one bond in particular. Opposite charges in a symmetrical molecule negate each other. So what's important here is the symmetry of the molecule shape. Water is polar, so this is our water molecule, because both bonds are polar. So they're pulling electrons strongly to this oxygen atom. And the bent shape, which is asymmetrical of the molecule, causes one positive side and one negative side. So here's our positive side because the electrons are being pulled away from hydrogen. And this is the negative side because oxygen is pulling the electrons more strongly. And because this molecule is asymmetrical and all of the electrons are being pulled towards oxygen in this one direction, it's going to be a polar molecule overall. Carbon dioxide, on the other hand, is a nonpolar molecule. Even though both bonds are polar, because oxygen is pulling more strongly on the electrons than carbon, so technically we have a stronger pull of electrons towards this direction. They are equal because there's, again, electrons being pulled this direction from this bond. And because it has a linear shape, which is symmetrical, we're going to say cancel each other out, basically. These charges are balanced. And so this overall molecule is actually going to be nonpolar even though it's made of polar bonds because of the overall shape of the molecule. In summary, the electronegativity of the atoms in a bond can determine whether the electrons are shared equally, as in a nonpolar bond, or unevenly, as in a polar bond. A symmetrical molecule with polar bonds may still be nonpolar overall. So far, we've been discussing the forces or bonds that hold molecules together, so individual atoms. But what forces hold the whole compound together, all the individual molecules in a compound? Well, the glue that holds a molecular compound together is called an intramolecular force. This is a polar or nonpolar bond. So this is what we've been discussing so far. Intramolecular means within a molecule. So within this hydrogen and chlorine bond, within this molecule is an intramolecular force, a polar bond that's holding them together. The forces that hold one molecule to another molecule, though, in a solid or a liquid are called intermolecular forces. So intermolecular means between molecules. So this is within molecules. Intermolecular is between molecules. So these are the forces that hold one whole molecule to another whole molecule. These forces are strong within the molecule, but the intermolecular forces are weak. Or weaker, I should say. Certainly much weaker than the intramolecular forces. So how strong are these intermolecular forces, which we abbreviate as IMFs? Well, there are 3 types, and they have a variety of strengths. First is the dispersion force. And this occurs in all covalently bonded molecules, even nonpolar ones. And these are weak forces caused by the temporary movement of electrons. These are usually the weakest intermolecular forces, unless there are a lot of electrons in the molecule. For example, if it's a very large molecule. So let's look at this dispersion force. So these oxygen molecules are diatomic, and because they're made of the same atom, they are completely nonpolar. But as these electrons orbit around the nucleus of the oxygen molecules, they become more densely located at some points, causing a slightly negative charge on one side or a slightly positive charge on the other side, just as they are moving around the nucleus. And so that can allow these molecules to be attracted to each other in a very weak way, as the slightly positive side of one is attracted to the less dense electron portion of another. Dipole-dipole forces are another type of intermolecular force, and they occur between polar molecules. This is an attraction between polar molecules where the positive side of one molecule is attracted to the negative side of another molecule. The strength of these forces is dependent on the polarity and the size of the molecule. So unlike the dispersion forces where we're talking about just electrons moving and where exactly they are located around the nucleus, these are polar bonds. So one side of the molecule is actually more negative than the other side of the molecule, as we've talked about in polar bonds before. And so the slightly negative side of one of those molecules is attracted to the slightly negative side of another. And these are a little bit stronger than the dispersion forces, but they are dependent on the polarity of the molecule. So if this is a very strong polar bond in this molecule, then one side is going to be more strongly polarized, and that's going to make this attraction stronger. And smaller molecules have a stronger attraction here as well. Larger molecules don't experience the dipole forces quite as strongly because they have a lot of other forces going on within the molecules. Hydrogen bonding is a special case of a dipole-dipole force. It occurs between molecules where hydrogen is covalently bonded to a fluorine, oxygen, or nitrogen in one molecule and attracted to a fluorine, oxygen, or nitrogen in a neighboring molecule. So I alluded to this before. If we're talking about water molecules here, which is definitely a type of hydrogen bonding, because the hydrogen is covalently bonded to a fluorine, oxygen, or nitrogen because they have very high electronegativity values. And so this is going to be a very strong polar covalent bond. And that allows the two sides of this molecule to be quite polar. And because of the molecular shape, the bent molecular shape, the two sides of this molecule are quite polarized. And there can be an attraction then from the slightly positive side of one of these molecules to the slightly negative side of another molecule. And hydrogen bonding between water molecules is, as I said, an important reason for the unique properties of water. And hydrogen bonds are the strongest type of intermolecular force. So how do intermolecular forces affect a compound's properties? Well, the stronger the intermolecular forces, the more energy it takes to break apart the molecules. This leads to higher melting points, higher boiling points, and increased viscosity. So melting points and boiling points here, obviously we're breaking the bonds between the molecules in order to either allow them to slide over each other if they're becoming liquids, or to break apart from each other into a gas form. And so those molecules need to be able to separate from each other. The stronger the intermolecular forces, the harder time they're going to have separating from each other. So then that'll cause a higher melting point and a higher boiling point. And viscosity is the thickness of a liquid. Honey, for example, is a very viscous liquid caused by those intermolecular forces attracting the molecules together and keeping it in sort of a slightly solid form. They're much thicker because those molecules are being attracted to each other rather than just easily sliding past each other. In summary, intramolecular forces occur within a molecule, but intermolecular forces occur between different molecules. Intermolecular forces are dependent on the molecule size and polarity and vary in strength. Intermolecular forces can affect the properties of a compound.